Section 2.6, it's all about the inverse of a matrix. So to get started, we'll talk about the identity matrix, which is down here. But before we get to the identity matrix, let's look at it with real numbers. In the set of real numbers, there's an identity element for multiplication. There's one for addition. It'd be 0 for addition. But for multiplication, it's 1, the number 1. And that's true because if you take 1 times 4, for example, it equals 4. And then you can reverse it on the other side. 4 times 1 is also equal to 4. 1 here is called the identity element for multiplication, because you can multiply any real number by the identity element 1, and you'll get that same real number back. Alright, so now let's look at it with matrices. It's got to be all identity matrices are square. So a square matrix, it's got to have 1s along the main diagonal and 0s everywhere else. So for a 3 by 3 looks like this. Remember, this is the main diagonal, so it should have 1s on it and then 0s at all the other entries. Alright, so let's test out this theory with, let's look at this 2 by 2, and then we're going to multiply by the identity matrix on either side and see what we get. We should get this matrix back, but let's check it out. Alright, let's start with, this matrix. 3, 6, negative 2, and 5. Let's multiply by the identity matrix on the right, see what we get. Okay, we did matrix multiplication in 2.5. So remember, we're going to multiply these with their dot products. We're going to take the rows of the first matrix dotted with the columns of the second matrix. Alright, so in the 1, 1 position of our product matrix, we're going to dot row 1 with column 1. That's 3 times 1 is 3, plus negative 2 times 0, which is 0, so that's just going to be a 3. In the 1, 2 position, that's row 1 dotted with column 2, 3 times 0 is 0. Negative 2 times 1 is negative 2, goes there. This is the 2, 1 position, row 2, column 1, 6 times 1 is 6, plus 5 times 0, that'll be a 6. And then row 2, column 2, 6 times 0 is 0, 5 times 1 is 5. Alright, so this is that same matrix again. Let's try it on the other side. Try it with 1, 0, 0, and we should get the same thing. Let's double check. 3, negative 2, 6, and 5. Alright, this time we're going to take the rows from here and the columns from here. Alright, going across row 1, dotted with column 1. 3 times 1 is 3, plus 0 times 6. That's a 3. Row 1, column 2. 1 times negative 2 is negative 2. 0 times 5 is 0. It's a negative 2. Row 2, column 1. 3 times 0 is 0. Plus 1 times 6. And then row 2, dotted with column 2. 0 times negative 2 is 0. 1 times 5 is 5. Right? So it checks out. That's the identity matrix. The 1s along the main diagonal and 0s everywhere else. Alright, inverses. Gosh, where do I have my, I don't know why that's way down there. It's okay anyway, I've got inverses up here, but I talk about it way down here. In the set of real numbers, again, let's go back to real numbers before we expand it to matrices. Look at 4 and 1/4. Again, we're looking at inverses, not additive inverses, but multiplicative inverses. Same as reciprocals here. Set of real numbers 4 and 1/4 are inverses, since if you take 4, multiply it by its multiplicative inverse, you're going to get the identity element. Same on the other side if you flip them around. 4 times 1/4 is 1, or if you take 1/4 times 4, it's 1. You know multiplication is commutative, so either way you multiply it, still get the same answer. Alright, so for matrices, 2 matrices are inverses if A times B equals I, the identity matrix, and vice versa, B times A equals the identity matrix. And then B is going to be called the inverse of A, and it's denoted with This looks like an exponent of -1. It's just written as a superscript, really. This doesn't mean 1 over a. That means a inverse. It's just notation, right? Denoting the inverse of a to the -1. We will call it a inverse. Okay, only square matrices can have inverses. They have to be square matrices. All right, in order for to have an inverse, first of all, it has to be square, but not all square matrices have inverses. All right, just because it's square doesn't mean that inverse exists. But if the matrix does have an inverse, it's got to be square to begin with. All right, let's look at this example, and we've got a matrix A and a matrix B. And here we're going to determine whether B is the inverse of A. All right, whether these are inverses of each other. So to do that, we're going to have to multiply these two together. And let's see. Let's do A times B. All right, let's look at the dot products. And I'm going to write this out. 3 times 2 is going to be 6, and 5 times a -1 is going to be -5. Right, that's in that 1, 1 position. That was one row. Row 1 dotted with column 1. Then, when we do row 1 dotted with column 2, row 1 dotted with column 2, we've got 3 times a -5 halves, yes, -15 over 2, and then 5 times the 3 halves there. We're going to have to add that to 15 over 2. All right, and let's go down. Row 2 dotted with column 1, 2 times 2 is 4, plus 4 times a -1 will be -4. And then this last one down here, 2 times a -5 halves, that's going to be -5, and 4 times 3 over 2 is going to be a +6. All right, let's see what all that equals. 6 minus 5 is a 1. This zeroes out. 4 minus 4 is 0, and -5 plus 6 is 1. So that's the identity matrix. So really, it will suffice if you just check it on one side. If you want to do it overkill, you can do B times A. But if you check it on one side and it works, then it will absolutely work on the other side as well. You really just need to check the one side. All right. Yeah, so here we would say yes. The answer here would say yes, B is the inverse of A, and A is the inverse of B as well. All right, yeah, that's all well and good if they give you the two matrices and they say, okay, are these inverses? All you do is multiply them, see if you get the identity matrix. If it was anything else, if one of these entries were different, you would say no, they're not. All right, but what if they just give you a matrix and they say, okay, now find the inverse of this matrix? What you do is augment the given matrix with the corresponding identity matrix, and then use Gauss-Jordan method for row reduction. So what you're going to do is you're going to have your matrix A over here, and you're going to augment it with the identity matrix of the same size. And then you're going to use a Gauss-Jordan method, and you're going to end up with the identity matrix on this side, and what pops up on the right is going to be your inverse matrix. So that's the process. Let's actually do one and see how it shakes out. Here, start with the 2 by 2. It says find the inverse of this matrix A. Alright, it's a nice little 2 by 2. So, to get started, it says to augment that matrix to -7, -1, 4. We want to augment it with the corresponding identity matrix of the same size. Alright, now we want to do Gauss-Jordan method for row reduction. Remember, we want to start with a 1 up here in the 1, 1 position. And I already have a negative 1 down here, so I'm going to flip-flop rows, and I'm going to take the opposite of this. So let's take the opposite of row 2 and switch places with row 1. Alright, so the opposite of row 2 is going to be a positive 1, a negative 4, a 0, and a negative 1. And let's just put that other row 1 down here. Like that. See, all we did was we wrote this row 1 down here, and this one came up here, but we took the opposite of it. Okay, very good. So that got me a 1 there. Remember, the very, very first time you get a 1 in that 1, 1 position, you can flip rows if it helps you out. Right, that's better so I didn't have to deal with fractions right here, dividing everything by 2. Okay, so I got a 1 there. Now I need a 0 down here. And remember, you're going to use that leading 1 to get a 0 down here. So let's take negative 2 times row 1. We're going to add it to row 2 to replace row 2 for a new row 2. Alright, let's write that down here. So row 1 is going to stay the same. What I'm going to do to get this new row 2, remember we're replacing row 2, negative 2 times this whole row and add it. So negative 2 times 1 is a negative 2 plus 2 is 0. That's what I wanted. So I wanted a 0 there. Negative 2 times a negative 4 is a positive 8. And if I add negative 7 to that, I'll get a 1. Alright, if I take negative 2 times 0, I'll have 0 plus 1. That 1 stays there. And negative 2 times negative 1 is a 2 plus 0. 2 goes down there. It's very nice. Alright, it's nice because, look, I already have my 1 in the position that I wanted. Alright, my 1 along the main diagonal. Column 1 is straight, go to column 2. In that 2, 2 position, the 1's already there. So I just need to make this a 0. Let's take 4 times row 2 plus row 1, and I'm going to replace row 1. So row 2 stays fixed. Okay, I'm changing row 1 now. 4 times 0 is 0, plus 1 is 1. Didn't want to change it, didn't change. 4 times 1 is 4, plus a negative 4 is 0. That's what I wanted. Alright, then 4 times 1 is 4 plus 0. That becomes a 4. And 4 times 2 is 8, plus a negative 1 is 7. Okay, so this is the inverse of matrix A, and it looks like this. 4, 7, 1, 2. Alright, this is the answer. So, it's not too bad. Sometimes you'll have to deal with some fractions, but it shouldn't be anything too hairy, anything too yuck. And to find the inverse of a matrix, you augment that matrix with its corresponding identity matrix, just like we did in that previous example, and then do Gauss-Jordan method for row reduction to get the identity on the left, and then what pops up on the right is your inverse. Look at this note down here. When you're reducing, once you are trying to find the inverse, and you're going along doing your Gauss-Jordan method correctly, if a row of zeros pops up on just this left-hand side, doesn't matter what's on the right, if everything zeroes out on the left-hand side, automatically you need to stop right there and say the inverse does not exist. I think in the homework that might happen to you, so watch out for that. Okay, I'm going to stop this video here and then we'll talk about matrix equations in the next one.